Let's now look at the effect of the nucleophile on the SN2 reaction. Once again, remember that the nucleophile does appear in the rate law of the SN2 reaction, so the rate is going to be responsive to changes in the nucleophile. And we'll find that SN2 reactions work best with strong nucleophiles. So unlike the SN1 reaction where the identity of the nucleophile did not matter because it didn't play a role in the rate determining step, SN2 reactions are going to be dependent on the identity and the concentration of that nucleophile. We already talked about a couple of strong nucleophiles. So these hydroxides, the alkoxides, those are very strong. But here are a few others. Negatively charged nitrogen nucleophiles or negatively charged carbon nucleophiles are going to be examples of very strong nucleophiles. And we also have some species that might be weak bases but can act as strong nucleophiles because they have a lot of electron density. So for example, sulfur anions like SH- or SR- are very strong nucleophiles, but weak bases. The same thing with something like an acetate ion, CN- or N3-, which has a structure like this. These are all going to be, and this is called azide, by the way. These are all going to be examples of strong nucleophiles that are weak bases. The halogens are also weak bases, but good nucleophiles, particularly chloride ion, bromide ion, and iodide ion. If we were to run an SN2 type reaction under these two different conditions, so the first being just neutral water displacing the chlorine here versus hydroxide ion displacing the chlorine, you would see that the stronger nucleophile, the hydroxide, would lead to a much faster rate of reaction. And this is different than what we saw with the SN1 reaction, where if you started with the tertiary halide, there would be no difference in rate in these two conditions. Just a few more notes about the trends in nucleophilicity. In aprotic solvent, if you're going down a group, like the halogens, for example, you should recall that you have a decrease in basicity, and therefore you should also have a decrease in nucleophilicity. This trend changes, though, when you put those same halogens into a protic solvent. The basicity still is decreasing. However, the nucleophilicity is increasing when you're in the protic solvent. And the reason for that has to do with the size and how well the ion is solvated. So if you're in protic solvent, something like fluoride ion, which is very small, is going to be highly solvated, and so it's not going to be able to act very well as a nucleophile. However, the much larger iodide ion is going to be less solvated, and so it will be better able to act as a nucleophile. So this is one key difference between bases and nucleophiles. The nucleophilicity does have a dependence on the sterics of the nucleophile, and so the solvent, when it's highly solvated, that's going to play a role in how sterically hindered the nucleophile is.